Theory of relativity, being theory of space, time, and gravity, provides the theoretical framework for modern cosmology. Here I will assume, for the purpose of this class, that you actually know something about this. And here is just a quick refresher. The special theory of relativity, which came first, postulates that all inertial, unaccelerated frames of references must be equivalent. And that has a number of important consequences. It does unify space and time in a novel fashion. It postulates the speed of light is the maximum speed that can be had in a space-time, or rather, light moves at the maximum possible speed. It predicts Lorentz contraction and time dilation. Those are two important concepts, and if you don't know what they are, you really need to look them up. And of course, it predicts the equivalence of mass and energy, the famous E equals mc squared formula, as well as a number of other effects. Here is the front page of Einstein's original special relativity paper from 1905. The special theory of relativity is limited in its application because it talks only about unaccelerated frames of references. What happens with accelerated ones? Well, this is where general theory of relativity is. Einstein finished that in 1915, and that was an even more important change in our view of space-time. Here it's assumed that all frames of references are equivalent. And through equivalence principle that gravitational mass and inertial mass are the same. A one-sentence summary of what general relativity says is that the presence of mass or energy, which remember are equivalent, determine the local geometry of space. And local geometry of space determines where would mass and energy move. The two have to be computed in a consistent fashion, and that is what general relativity is all about. So general relativity introduced curvature of space, which also then immediately had predictions of light bending and gravitational field and so on. Here is the front page of Einstein's general theory of relativity paper. However, even before this was published, he already had some of these ideas, including gravitational bending of light. The equivalence principle postulates that gravitational and inertial mass are the same. In addition to that, there is Mach's principle, which postulates that gravitational interaction of all masses is what creates inertia. In an empty universe, there will be no inertia, there will be no mass, which is sort of obvious. But Einstein argued that gravity is an inertial force, and there is famous experiment with elevators and rockets. There are two important consequences of the equivalence principle. First, that light should be blue-shifted coming into gravitational potential wells and red-shifted coming out of the gravitational potential wells. And the light path will be curved in space in general. The presence of mass will introduce local curvature, and light moves to whatever is the shortest line. Einstein was already aware of the possibility of gravitational bending of light. And in 1911, he wrote to George Ellery Hale, famous astronomer, asking him if this can be observed. Well, apparently it wasn't possible at the time. However, it was actually possible to do it during solar eclipses. And there is a famous experiment where Eddington and collaborators measured positions of stars around solar disk during the maximum eclipse, and then compared them to when the sun is somewhere else in the sky. This completely confirmed Einstein's prediction of bending of light by about almost 2 arc seconds near the edge of the solar disk. And this is where Einstein really became famous. So let's talk a little bit about geometry of space-time. In general, space can be curved. It's hard to draw four-dimensional space-time, so we use these two-dimensional analogies embedded in three-dimensional space. Positive curvature is like curvature of a sphere, and that corresponds to the so-called closed universe. The curvature will depend on the amount of mass and energy that's present. If it's exact right critical amount, it'll be a flat geometry, the familiar space. If it's less than that, it'll be hyperbolic geometry, which is also open in extends to infinity. So how do we quantify geometry of space? The most general approach is to define a metric, which is a formula that gives the distance between any 2 points, and it's usually expressed in form of quadrature, like here. That is the sum of products of increments in each of the 2 coordinates multiplied together, summed over all of them with some coefficients multiplying them. So these coefficients are the metric tensor, and its indices in four-dimensional space-time run from 0 to 3. 0 is the time, 1, 2, and 3 are usual spatial xyz dimensions. This is a matrix, 4 by 4, or tensor, if you're familiar with that. And for your plain familiar geometry, the coefficients are 1 on diagonal. It's the sum of squares in increments in 3 spatial coordinates, and all off-diagonal elements are 0. So this is the simple measure of distance in 3D space. But in general, it can be different, and values of these coefficients can be derived from general theory of relativity. So if we know what the metric is, then geometry is completely specified by it. In the special relativistic space, which is still flat and Euclidean, you have to introduce the time element, and for reasons that we don't need to go into, it is expressed as square of the time increment minus the spatial increment of quadratic sum in 3 coordinates. But the very general case in general relativity for homogeneous and isotropic universe is the Robertson-Walker metric. Remember that we introduced homogeneity and isotropy as means of simplifying general relativity. Homogeneous universe means it's same everywhere and isotropic in all directions, and therefore only radial coordinate would matter. So now the Minkowski metric from above still has the same old time element, and then has a spatial element which is multiplied by a function, r of t, which is called a scale factor, and the rest of it is expression that is universally true for different values of spatial curvature. So Robertson-Walker metric is expressed in polar coordinates. This is useful because only radial direction matters, and it can be also written in this form, where that function s, depending on different curvature, is sine, hyperbolic sine, or the radius itself. Remember that that whole spatial increment can be changing in time, in principle, and this is what the scale factor is all about. Sometimes it's denoted as r of t, sometimes a of t. I'll be using both of those. You just have to pay attention. Basically, that's the ratio of any given distance at some time to what it was relative to a 0-point reference. Like if you start with an expanding universe with distance between two galaxies of a gigaparsec, then sometime later it will be more than a gigaparsec. So this is just a thumbnail sketch of what general relativity is all about. Next time we will talk a little bit more how it's applied in cosmology.